A perfect cosmic ring spins in the dark, 500 million light-years from Earth. This is the Cartwheel Galaxy, and its beautiful shape is a lie hiding chaos. By the end of this journey, you will understand how a single galactic catastrophe can rewrite the rules of the cosmos. We are about to dive into 25 of the strangest phenomena locked within this pinwheel, from the shockwave of its violent birth to the unearthly power sources glowing in its rings. What force could erase the heart of a galaxy, and what monstrous objects are being born in the aftermath? Which cosmic mystery do you think could challenge our science the most? That violent origin story is where our list truly begins. The first and most fundamental phenomenon of the Cartwheel Galaxy is the cataclysmic collision that forged its ring. This is not a story of two galaxies gently merging. It was a cosmic bullet, a smaller galaxy screaming through the heart of the Cartwheel hundreds of millions of years ago. Think of it not as a collision but as a perfect strike. The intruder did not hit the edge, it did not glance off. It plunged directly through the very center like a needle through a vinyl record. This precise, devastating impact sent a gravitational shockwave rippling outward through the entire galaxy. It is the ultimate bullseye effect. You can picture a stone dropped into a still pond, sending perfect circular waves racing to the edges. In the Cartwheel, that stone was an entire galaxy, and the waves were walls of gas and dust compressed to unimaginable densities. As this shockwave expanded, it swept up billions of stars and trillions of tons of interstellar material, pushing them all into a single, dense ring at the very outer frontier of the galaxy. That ring, glowing with newborn stars, is the brilliant wheel we see today. Every other strangeness we will uncover, from ghostly energies to missing pieces of the galactic core, traces its lineage back to this single, violent moment. The collision did not just reshape the galaxy, it reset its entire clock, triggering a frenzy of creation and destruction that is still unfolding. This foundational event is the key that unlocks every other door. That brilliant outer ring is only the first layer of this cosmic onion. Just inside its blazing light lies a second, far stranger structure. Phenomenon 2 is the ghostly inner ring and its diffuse halo. If the outer ring is a neon sign screaming with new life, the inner ring is a faded photograph of what came before. This pale, delicate circle of light sits much closer to the galaxy's troubled core. It is not made from the shockwave's compressed gas, but from the survivors. These are the older stars of the Cartwheel's original spiral disk, stars that were not swept up by the colossal gravitational wave. They were left behind, rearranged by the chaos into this faint, ethereal loop. It is a cosmic ghost, a memory of the galaxy's former self etched in starlight. This ring tells us the collision was not total destruction, it was a brutal editing. The old galaxy was not erased, it was rewritten. Now pull your view even further back. Encasing this entire two-ring system is Phenomenon 2's second part, the vast diffuse stellar halo. Imagine a sphere of faint, ancient stars and invisible dark matter that stretches far beyond the visible rings. This halo was always there, a quiet relic from the galaxy's earliest days, but the collision acted like a giant spoon, violently stirring this cosmic soup. The impact sent tremors through the halo, disturbing its ancient stars and churning up its dark matter. This invisible structure is the galaxy's final boundary, its outermost skin, and it holds clues to everything that was shaken loose during the catastrophe. So the Cartwheel is not just a ring, it is a set of Russian dolls, a brilliant ring of youth, a ghostly ring of memory, and a vast stirred halo of ancient history. Each layer tells a different chapter of the same violent story. The very heart of the Cartwheel Galaxy holds a profound emptiness. Phenomenon 3 is the missing central bulge. In a typical spiral galaxy like our own Milky Way, the core is a brilliant, crowded metropolis. Billions of ancient stars swarm together in a dense, spherical hub, creating a bright, unmistakable glow at the galaxy's center. But look into the middle of the cartwheel. That glow is strangely faint, almost anemic. The expected bustling stellar city is gone, replaced by a dimmer, more diffuse region. It is as if someone reached in and removed the galaxy's engine, leaving behind only a ghost of its former power. So what happened to the core? Astronomers see two chilling possibilities. The first is pure disruption. The smaller galaxy's bull's-eye shot through the center would have been like a gravitational bomb going off. The orderly orbits of billions of stars in the bulge would have been violently scrambled, flung outwards into the rings or sent drifting into the halo, leaving the center depleted. The second theory is even more direct. Perhaps the intruder did not just disrupt the bulge, it physically carved it out. As it passed through, its own gravity could have acted like a cosmic plow, scooping up vast swaths of the central stars and pulling them along in its wake, literally stealing the heart of the galaxy. This missing bulge is not just a curious detail, it is a fundamental challenge. Our models of how galaxies form and behave are built on stable, dense cores. The cartwheel's faint heart forces us to ask just how much damage can a collision do? It suggests the event was not merely a reshaping, but a near evisceration, leaving a wound in space where a galaxy's soul used to be. This central mystery makes every other strange feature seem even more extreme. These faint spokes between the rings are the galaxy's hidden skeleton. Phenomenon 4 is the mysterious radial spokes of dark matter. When you look closely at Hubble's images of the cartwheel, you see more than just two smooth rings of light. Stretching between the inner ghost ring and the outer blazing ring, like the spokes on a bicycle wheel, are faint, shadowy lines. They are radial, meaning they point directly from the center outwards. At first glance, you might think these are simple lanes of dust, just cosmic dirt obscuring the starlight. But they are something far stranger. These spokes are most likely density waves, ripples of compressed gas and dust frozen in time. Think of them as the cosmic equivalent of the grooves you see in the sand after a wave recedes from the shore. They are a permanent record of a passing force. In this case, the force was that initial, unimaginable shockwave from the collision. As that wall of energy expanded outward, it did not move as a perfectly smooth front. It churned and rippled, and in its wake, it left these radial patterns stamped into the interstellar medium, the thin soup of gas and dust between the stars. But here is where the mystery deepens. What is holding these delicate structures in place millions of years after the initial wave has passed? They should have dissolved, smeared out by the rotation of the galaxy. The leading theory points to an invisible hand. Many scientists believe these faint spokes are tracers, cosmic footprints, revealing the presence of the galaxy's underlying dark matter distribution. Dark matter is that mysterious, invisible substance that makes up most of a galaxy's mass, a gravitational glue that holds everything together. In the cartwheel, the collision would have violently shaken this dark matter halo, creating ripples and densities within it. The visible spokes we see in the gas and dust may be simply following this invisible scaffolding, pinned in place by the gravitational pull of dark matter concentrations we cannot see. So these are not just shadows, they are a map. They highlight the invisible architecture, the hidden skeleton of dark matter that is actively guiding and shaping the brilliant, visible form of the Cartwheel Galaxy. It is a stunning reminder that what we see shining in space is only a fraction of the story, a decoration draped over a framework we are still struggling to perceive. Scattered across those brilliant rings are points of light that defy all logic. Phenomenon 5 is the presence of ultra-luminous X-ray sources, cosmic powerhouses of unknown origin. These are not simply bright stars, they are pinpricks in the galaxy's fabric that pour out staggering, almost impossible amounts of X-ray energy. To understand why this is so strange, you need to know the limits. A typical stellar mass black hole formed from a collapsed star has a maximum brightness it can achieve as it pulls in material, a ceiling called the Eddington limit. The ultra-luminous X-ray sources in the Cartwheel blast through that ceiling. They shine with the X-ray power of millions of suns, output that should belong to the supermassive black holes lurking in the centers of galaxies, not to tiny points out in the spiral arms. So what are these impossible beacons? Astronomers are staring at two equally thrilling possibilities. The first is that we are finally seeing intermediate mass black holes in action. These are the cosmic missing link, black holes with masses hundreds to thousands of times greater than our Sun, far larger than a stellar corpse but smaller than a galactic monster. They have been theorized for decades but are incredibly hard to find. The violent, star-forming frenzy of the Cartwheel's rings may have created the perfect nursery for them, and their extreme X-ray glow could be the signature of their immense gravity feasting on surrounding gas. The second possibility is just as exotic. Perhaps these are not unusual black holes, but usual black holes in an unusual state. They could be binary star systems where a normal black hole is pulling material from a companion star at a super Eddington rate, gorging itself so violently that the radiation punches through the theoretical limits in a way we do not fully understand. Either answer points to the same terrifying conclusion. The collision that forged the Cartwheel did more than rearrange stars. It created a laboratory for the most extreme physics in the universe. These ultra-luminous X-ray sources are screaming at us that processes we have only guessed at are not just possible. They are happening right now in plain sight, rewriting the rules of how gravity and light behave under duress. They are the galaxy's way of showing us that its rings are not just nurseries for stars, but crucibles for cosmic monsters. But the light we see is only a fraction of the story. A deeper, invisible heat bathes the Cartwheel's outer ring. Phenomenon 6 is the mysterious infrared glow emanating from that brilliant band of stars. When astronomers point telescopes that see in infrared light, wavelengths longer than what our eyes can perceive, the Cartwheel's outer ring does not just shine, it blazes. This is the thermal signature of cosmic dust, trillions upon trillions of microscopic grains of silicon and carbon, the soot from the galaxy's great fire. These dust clouds are warmed by the fierce ultraviolet light from all those newborn massive stars, and they re-radiate that energy as a pervasive infrared glow. It is the same principle as asphalt heating up in the sun and giving off warmth you can feel with your skin but not see with your eyes. Yet the intensity of this glow holds a puzzle. Is it solely the heat from the visible stars, or is there something more hidden within those opaque dust clouds? This is where the mystery solidifies. Those vast dust clouds are not just blankets, they are curtains, obscuring entire chapters of the ring's violent activity from our optical telescopes. Behind that veil, astronomers suspect could be superstar clusters still swaddled in their birth cocoons, stellar nurseries so dense and active they would dwarf anything in our local universe. Or perhaps the earliest, most chaotic stages of star formation, where giant gas clouds are just beginning to collapse under their own weight. For decades, we could only guess at what lay behind this infrared shroud. Now a new eye has opened. The James Webb Space Telescope, built to see precisely in these infrared wavelengths, is our key to lifting that veil. Its piercing gaze can peer directly through the dust, seeing the heat signatures of objects hidden from Hubble's optical view. It can count the embedded stellar embryos, measure the temperatures of the densest gas clouds, and potentially spot the hidden power sources contributing to that overwhelming infrared glow. This is not just about seeing more stars, it is about witnessing the birth of the universe's most extreme environments in real time. The Cartwheel's infrared mystery is a locked door, and we have just been handed the key. What we find behind it may redefine how a galactic collision builds its new world. Dotted along that luminous outer ring are knots of light so intense they seem to burn holes in the fabric of space itself. Phenomenon 7 is the runaway star-forming regions, colossal factories of creation operating at a frenzied, unsustainable pace. While the entire ring is a stellar nursery, these are the mega-cities within it, specific areas where the process of star birth has gone into absolute overdrive. They appear as brilliant, fuzzy knots in telescope images, glowing with the combined fury of perhaps tens of thousands of newborn stars, many of them massive, hot, and destined for short, explosive lives. To grasp their scale, imagine our galaxy's most famous stellar nursery, the Orion Nebula. It is a bustling maternity ward giving birth to a few thousand stars. One of these knots in the cartwheel would be like 100 Orion nebulas crammed together into a single, seething cauldron of light. So why here? What triggers these specific superregions within an already supercharged ring? The answer lies in the chaotic aftermath of the collision. The initial shockwave compressed the galaxy's gas into that outer ring, but that gas was not smooth. It was lumpy, filled with denser clouds and vast empty voids. As the ring rotates, these giant clouds of hydrogen and dust are now crashing into each other at phenomenal speeds, their collisions triggering second, third, and fourth waves of compression within the larger compressed zone. It is like waves on a stormy sea colliding to create a towering rogue wave. Furthermore, the mysterious radial spokes of dark matter we discussed earlier may act as gravitational guides, funneling and concentrating this interstellar material into specific hotspots, creating the perfect, dense conditions for a star-forming frenzy. These runaway regions are more than just bright spots, they are cosmic pressure cookers. They allow us to study star formation under conditions we cannot replicate anywhere nearby, witnessing the birth of star clusters on a scale that likely dominated the early, violent universe. In these knots, we are watching the universe's most fundamental act of creation pushed to its absolute limit, a direct and spectacular consequence of a single, perfect strike. The gas clouds of the cartwheel are brewing a chemical cocktail unlike any other. Phenomenon 8 is the strange molecular makeup of its rings, a cosmic recipe rewritten by violence. When astronomers break the light from the galaxy into its component colors using spectroscopy, they are not just seeing brightness, they are reading a chemical fingerprint. Each molecule in those vast clouds of gas absorbs and emits light at very specific, unique wavelengths, leaving behind telltale lines in the spectrum like a barcode. In the cartwheel, that barcode is sending a bizarre message. The mix of molecules detected there is profoundly unusual. There might be a startling overabundance of certain complex organic molecules, the kind that are considered the precursors to the chemistry of life. Or perhaps there is a surprising absence of common molecules you would expect to find in a normal, quiescent spiral galaxy. So what could cause a galaxy's entire chemistry to change? The prime suspect is the same force that shaped its rings, the colossal shockwave from the collision. You can think of it as a cosmic pressure cooker on an unimaginable scale. That wave did not just push gas around, it superheated it, compressed it to incredible densities, and flooded it with intense radiation from all the new stars being born. These are the exact conditions on a galactic scale that chemists use in labs to trigger unusual reactions. The shockwave could have shattered common, stable molecules and forced their atoms into new, more exotic alliances. It could have provided the immense energy needed to forge complex carbon chains that would normally take eons to form in the quiet cold of interstellar space. This turns the cartwheel from a mere spectacle into a titanic natural laboratory. It is a petri dish light years across, where we can observe how the fundamental building blocks of chemistry and potentially life behave under the most extreme duress. Does chaos in the cosmos actually accelerate the creation of complexity? The galaxy's strange molecular signature suggests it might. This finding forces us to reconsider where in the universe the ingredients for life could arise. Perhaps it is not in the quiet, stable backwaters, but in the violent, transformative aftermath of catastrophe, where the very elements are reforged into something new. The galaxy's rings are not a placid river of stars, but a storm-tossed sea. Phenomenon 9 is the high-velocity gas clouds, rogue waves of matter screaming through the chaos at impossible speeds. When astronomers point their radio telescopes at the Cartwheel, they do not just see a smooth, rotating disk of hydrogen gas. They detect individual clouds, vast islands of matter, hurtling along at velocities that defy the simple, orderly rotation of the ring. Some are moving far too fast to be bound by the galaxy's gravity in a normal orbit, and others are even streaming outward as if trying to escape the galaxy entirely. So what cosmic slingshot is launching these titanic gas clouds into their frenzied flight? The evidence points to two violent sources, both born from the collision's legacy. The first is the relentless fury within the ring itself. Those runaway star-forming regions are not just creating stars, they are creating supernova. When a massive star reaches the end of its brief life, it does not fade quietly. It explodes with the force of a billion suns, a supernova. Such an explosion does not just create light, it acts as a titanic piston, violently shoving the surrounding gas cloud outward at thousands of kilometers per second. These high-velocity clouds could be the direct shrapnel from these ongoing stellar detonations, the breath of dying giants pushing against the fabric of their own galaxy. But there is an older, even more dramatic possibility. Some of these rogue clouds may not be products of the new stars, but relics of the original catastrophe. During the bullseye collision hundreds of millions of years ago, the gravitational chaos would have been unimaginable. Entire swaths of gas could have been caught in the turmoil, whipped around the intruding galaxy, or slingshotted by the complex interplay of gravity, and flung onto wild, chaotic trajectories that they are still following today. They are like boulders sent flying by a meteor impact, still tumbling through space long after the crater has formed. Tracking these high-velocity clouds is not just about cataloging speed, it is a forensic investigation. By mapping their paths, astronomers can trace the invisible lines of force and the hidden flows of energy rippling through the Cartwheel. Each cloud's trajectory is a clue, pointing back to the violent event that launched it, whether a recent supernova or the ancient collision itself. They are the galaxy's way of showing us that the aftermath of chaos is not stillness, but a permanent state of turbulent, high-energy motion, where even the clouds of gas are living projectiles in a cosmic shooting gallery. The chaos of the Cartwheel may have been a one-two punch. Phenomenon 10 is the compelling question of a second intruder galaxy. The story we have told so far is dramatic enough, a single bullseye collision that forged a perfect ring. But when astronomers map the entire system, they find the plot thickens. The Cartwheel is not floating alone in the void. It is part of a small group of galaxies, and one of its companions shows signs of being dangerously close, its shape already distorted by the Cartwheel's immense gravity. This is not the original intruder that passed through the center. That culprit is likely long gone, having sailed off into the darkness after delivering its devastating blow. This is a new character, a smaller galaxy now being slowly pulled apart in a gravitational tug-of-war. You can picture it as a cosmic vulture circling the wounded Cartwheel, perhaps drawn in by the aftermath of the first collision. Its presence could explain some of the asymmetries in the Cartwheel's brilliant rings, subtle kinks and warps that a single, clean shockwave might not create. More importantly, this ongoing interaction could be responsible for recent, localized bursts of star formation, like fresh sparks being thrown onto an already raging fire. The gravitational pull of this second companion could be stirring the gas in the outer ring, triggering new rounds of cloud collisions and stellar births in specific hotspots. So we must ask, is the Cartwheel's trauma a single, catastrophic event or an ongoing saga? The evidence tilts toward the latter. This galaxy may be suffering from multiple galactic hits, a primary collision that set the stage and a secondary harassment that continues to poke and prod its recovery. This realization adds a profound layer of complexity to its history. It means the cartwheel is not a static monument to a past violence, but a dynamic, evolving system still very much in the throes of change. Its future evolution becomes even more unpredictable. Will this second companion eventually merge, adding more fuel to the stellar fire? Or will it be torn apart, its stars becoming a new stream in the cartwheel's vast halo? The presence of this possible second intruder turns a simple mystery into a layered cosmic drama, where the aftermath of one disaster actively sets the stage for the next. The perpetrator of this cosmic crime is still missing. Phenomenon 11 is the fate of the intruder galaxy itself, the celestial bullet that fired through the cartwheel's heart and then vanished. Where did it go? This is a galactic whodunit, and astronomers are the detectives scanning the scene for the fleeing suspect. They have identified a few likely candidates in the vicinity, smaller galaxies that show signs of being gravitationally disturbed, their shapes stretched and warped as if they recently survived a violent encounter. By measuring the speed and direction of these possible perpetrators, scientists can effectively rewind the cosmic clock. If a galaxy is moving away from the cartwheel at a certain velocity, they can calculate how long ago it would have been at the scene of the crime, providing a crucial date for the collision. It is like finding tire tracks leading away from an impact crater and using their depth and direction to estimate the speed of the vehicle and the time of the crash. This forensic astronomy allows us to piece together the exact dynamics of that fateful moment, understanding not just the damage but the angle and the force of the blow. Yet there is another, more chilling possibility. Perhaps the intruder did not escape at all. The gravitational forces during such a close, central pass are titanic. The smaller galaxy may have been completely torn asunder, shredded by the cartwheel's gravity, its stars and dark matter scattered and swallowed. If this is the case, then the culprit is not fleeing the scene, it is the scene. Its remains are now dissolved into the cartwheel's vast, diffuse halo, a billion stellar ghosts haunting the outskirts of the ring they helped create. This would be the ultimate galactic ghost story, written not in words but in the subtle motions and chemical signatures of stars that do not belong. So the search continues, a quest to find a galaxy that may no longer exist as we know it, its identity erased by the very catastrophe it caused. Whether it escaped or was consumed, its legacy is undeniable, etched in fire across 500 million light-years of space. The cartwheel's magnetic fields are a ghostly web of cosmic power. Phenomenon 12 is the discovery of unusual magnetic field structures woven throughout its brilliant rings. Magnetic fields are the universe's invisible skeletons, silent forces that can guide the flow of gas, steer the paths of charged particles, and shape the destiny of entire galaxies. In most spiral galaxies, these fields are tangled and chaotic, following the turbulent swirl of the arms. But recent radio telescope data from the cartwheel tells a different story. Here, the magnetic fields appear highly ordered and tremendously amplified. They seem to have been stretched and combed straight, aligned with the expansion of the ring itself. Imagine the galaxy's magnetic field as a bowl of invisible spaghetti before the collision, a jumbled mess. The colossal shockwave acted like a giant fork, pulling that spaghetti outward in long, straight strands that now run along the length of the expanding ring. This alignment is a permanent scar from the violence, a fossil magnetic field frozen in the moment of the ring's creation. But these are not passive scars, they are active forces. A magnetic field this strong and ordered can have profound effects. First, it can influence star formation itself. These fields create a kind of cosmic rigidity within the gas clouds. They can provide support against gravity, potentially slowing down the collapse of clouds into stars, or they can channel flows of material, directing where and how stars are born. Second, these amplified fields are perfect accelerators for cosmic rays, those high-energy particles that streak across the universe at nearly the speed of light. The orderly magnetic field lines can act like a vast galactic particle accelerator, whipping protons and electrons to incredible energies. Third, and perhaps most importantly, these magnetic structures will shape the galaxy's long-term evolution. They govern how energy is transported, how supernova shocks propagate, and how the galaxy interacts with the thin intergalactic medium around it. They are a fundamental part of the engine driving the Cartwheel's recovery. Yet measuring these invisible fields is one of astronomy's greatest challenges. We cannot see them directly. We can only infer their presence and strength by studying the polarization of radio waves emitted by electrons spiraling along the magnetic lines. Every faint signal from the Cartwheel is therefore a precious clue, a whisper from an invisible architecture that may ultimately hold the entire ringed structure together. This hidden magnetic skeleton proves that the collision's impact was not just gravitational. It was electromagnetic, rewriting one of the most fundamental forces in its corner of the cosmos. The Cartwheel's rings hold cities of stars. Phenomenon 13 is the population of superstar clusters, entire metropolises of light bound together by gravity. These are not the loose, open clusters we see in our own galaxy's spiral arms. They are colossal, dense balls of stars, each containing millions of members packed into a region of space that would barely stretch from our Sun to its nearest stellar neighbor. In our cosmic neighborhood, the only objects that come close to this scale are the ancient globular clusters, spherical swarms of stars that orbit the Milky Way like distant, fossilized bees. The superstar clusters in the Cartwheel are likely the infant versions of these ancient relics caught in the act of formation. So why does this violent ring produce them with such staggering efficiency? The answer is all about pressure. The initial shockwave from the collision did more than just sweep gas outward. It compressed that gas to densities far beyond what is found in a normal, peaceful galaxy. You can think of the interstellar gas clouds in the Cartwheel as being put through a cosmic trash compactor on a galactic scale. When a gas cloud is that incredibly dense, the process of star formation does not create one star at a time. It triggers a chain reaction, a runaway collapse that spawns hundreds of thousands, even millions, of stars almost simultaneously, all from the same colossal cloud. The resulting cluster is so tightly packed and massive that its own gravity binds it together permanently, preventing the stars from drifting apart. Studying these superstar clusters is like finding a living fossil. In our own Milky Way, the globular clusters are all ancient, over 10 billion years old, their fiery youth long since cooled into a steady red glow. Their formation era during the chaotic early universe is a closed book, but here in the Cartwheel, that book is open. We are witnessing that same violent, cluster-forming process happening right now in real time. It offers us a direct window into how the most ancient structures in our own galaxy were forged in an era of frequent collisions and cosmic turmoil. These brilliant knots are not just features of the Cartwheel, they are time machines showing us the violent birth of the stellar fossils that still silently orbit our own galactic home. Beyond even the X-rays lies a realm of pure energy. Phenomenon 14 is the tantalizing search for gamma-ray mysteries within the Cartwheel Galaxy. Gamma rays are the most energetic form of light in the universe, photons born from the absolute extremes of physics, from matter annihilating antimatter, from particles accelerated to nearly the speed of light and then violently slammed to a stop. They are the universe's final, most powerful scream. While no definitive detection of the Cartwheel in gamma rays has been confirmed, many astrophysicists believe it is only a matter of time. They look at the galaxy's contents, at those ultra-luminous X-ray sources and the countless supernova remnants, and see the perfect engines for such high-energy production. An ultra-luminous X-ray source with its intense gravitational and magnetic fields could be acting like a cosmic cannon, firing jets of charged particles at relativistic speeds. When those jets plow into the surrounding gas clouds, the resulting collisions could easily generate brief, brilliant flashes of gamma-ray light. Similarly, the shock waves from supernova explosions expand at thousands of kilometers per second, creating ideal natural accelerators for protons and electrons. When these accelerated particles interact, they too can produce gamma rays. The entire outer ring, with its continuous storm of stellar birth and death, could be shimmering with this invisible high-energy glow. To hunt for these signals, scientists turn to instruments like the Fermi Gamma Ray Space Telescope. Fermi does not see the sky as we do, it sees a map of violence. It scans the entire heavens, patiently collecting these rare, high-energy photons over years, building up a statistical picture. A clear gamma ray signal from the Cartwheel's coordinates would be a monumental breakthrough. It would not just tell us the galaxy is energetic, it would act as a precise cosmic pinpointer. Each flash would highlight the exact location where particles are being accelerated to near light speed, identifying the most powerful engines within the chaos. It would transform our view of the Cartwheel from a beautiful ring of stars into a visible, galaxy-sized particle accelerator, a place where the fundamental laws of physics are stress-tested under conditions we could never hope to recreate on Earth. The search continues, a silent vigil for the universe's most powerful whispers, waiting for the Cartwheel to reveal its ultimate energy. A perfect circle is a beautiful illusion. Phenomenon 15 is the subtle but undeniable asymmetry of the Cartwheel's brilliant ring. When you examine high-resolution images, you notice it is not a flawless geometric shape. One side of the outer ring often appears slightly brighter, more knotted with star-forming regions, or perhaps a little more extended and diffuse than the opposite side. It is as if the cosmic wheel has a heavier, more active half, throwing its perfect symmetry off balance. This is not a flaw in the image, it is a vital clue written in starlight, telling us the simple story of a single, clean bullseye collision is only an approximation. The real event was far messier, far more dynamic. So what could cause such a lopsided result in a structure born from a symmetrical shock wave? Astronomers point to several compelling factors, each adding a layer of complexity to the catastrophe. First, consider the angle of the original impact. While we describe it as a bullseye, the smaller galaxy likely did not hit the Cartwheel's center at a perfect 90-degree angle relative to its disk. It probably struck at a slight skew, like a bullet hitting a spinning coin not quite dead center. This would have imparted a slight twist to the expanding shock wave, causing it to compress the gas more forcefully on one side than the other from the very beginning. Second, we must factor in the influence of the companion galaxies, that possible second intruder still lingering nearby. Its gravitational pull is not uniform, it tugs more strongly on the side of the Cartwheel closest to it. This ongoing harassment can stretch and distort the ring, pulling one segment outward or funneling extra gas into it, sparking more intense star formation on that specific flank. Finally, the raw material itself was not uniform. The interstellar medium of the original spiral galaxy was not a smooth soup, it was lumpy, filled with giant molecular clouds and vast empty bubbles. When the shockwave expanded, it would have encountered these pre-existing uneven densities. It is like a wave hitting a rocky coastline versus a sandy beach. The resistance and the resulting splash are completely different. The shockwave would have compressed dense clouds more effectively, leading to brighter star formation there, while sailing more easily through thinner regions. This asymmetry is therefore a forensic record. By studying which side is brighter and how it is distorted, scientists can work backwards. They can estimate the angle of the incoming galaxy, gauge the strength of the companion's gravitational pull, and even map the ancient distribution of gas in the galaxy that died to create this ring. It proves the Cartwheel is not a static museum piece of a single event, but a dynamic, unbalanced system still reeling from a complex series of violent interactions. Its perfect ring a beautiful lie that hides a much more turbulent truth. The Cartwheel's brilliance is a snapshot of a single moment in an unending cosmic drama. Phenomenon 16 is the hunt for variable and transient objects, the sudden flares and disappearances that prove this galaxy is alive. Unlike the ancient, steady glow of most galaxies, the Cartwheel is a hive of frantic stellar activity, a place where things do not just exist, they happen. Astronomers do not simply take a single picture and move on. They monitor it for changes night after night, year after year, watching for the telltale flickers that signal a cosmic event unfolding in real time. The ultimate prize would be catching a supernova within the ring itself. In a galaxy forming stars at such a ferocious rate, massive stars are being born and dying constantly. A supernova in the Cartwheel would not be a subtle event. It would be a stellar detonation visible across intergalactic space, a new point of light flaring with the intensity of billions of suns before slowly fading over weeks or months. Witnessing such an explosion would give us a front-row seat to the death of a giant star in an environment utterly alien to our own, allowing us to study the physics of the blast and the elemental debris it scatters into the surrounding gas. But supernovae are not the only flashes in the dark. There is a quieter, more elusive class of event that astronomers also hope to find: microlensing. This occurs when a dark, compact object like a rogue planet, a neutron star, or a lone black hole drifts directly between our telescope and a background star in the Cartwheel's ring. The foreground object's gravity acts as a natural magnifying glass, bending and amplifying the light of the distant star for a brief period, causing it to brighten and then dim in a very specific, predictable pattern. Detecting a microlensing event here would be a monumental discovery. It would not just be about the brightening star, it would be a direct detection of an invisible wanderer. By analyzing the light curve, the precise way the star brightens and fades, scientists could estimate the mass of the lensing object. This is how we could find free-floating planets cast adrift from their solar systems by the galaxy's violent past, or isolate stellar mass black holes drifting silently through the darkness. Each successful detection, whether a titanic supernova or a subtle microlensing flicker, transforms the Cartwheel from a static portrait into a dynamic movie. It reminds us that we are not looking at a fossil, but at a living, breathing, and violently changing ecosystem on a galactic scale, where new stories are written in light every single day. Even the most basic fact about the Cartwheel Galaxy is a subject of intense debate. Phenomenon 17 is the fundamental challenge of measuring its distance, a cosmic yardstick that keeps shifting. You might think that in an age of advanced telescopes, knowing how far away something is would be a settled matter. For the Cartwheel, it is anything but. Different scientific techniques have returned different answers, placing it roughly 400 million light-years from Earth in some calculations, and closer to 500 million in others. That 100 million light-year gap is not a small margin of error. It is a chasm of uncertainty wider than our entire local group of galaxies. This discrepancy is far more than a technical footnote. It strikes at the heart of everything we are trying to understand. Think of it this way: if you misjudge the distance to a street lamp, you also misjudge its true brightness and size. The same principle applies on a galactic scale. Pin down the correct distance and you can calculate the Cartwheel's true physical diameter. Is its brilliant ring 150,000 light-years across, or is it closer to 200,000? That changes our perception of its sheer scale. More critically, distance determines luminosity, the energy output of those ultra-luminous X-ray sources, the total infrared glow from the dust, the ferocious rate of star formation. All of these numbers are calculated based on how far away we believe the galaxy to be. A more distant Cartwheel means every single one of its phenomena is intrinsically more powerful and more energetic than we thought, because its light had to travel farther and dim more to reach us. Most importantly, the distance directly ties to the timing of the catastrophic collision itself. By measuring the motions of the suspected intruder galaxies and the expansion of the ring, astronomers can rewind the cosmic film. But to know when the collision happened, they need to know where it happened. A difference of 100 million light-years in distance translates to a difference of tens of millions of years in the estimated age of the ring. Was this catastrophe recent in cosmic terms, or did it occur in a much more ancient epoch? This meta-mystery reveals a humbling truth. Before we can even begin to unravel the galaxy's exotic physics, we must first solve the most fundamental problem in astronomy, figuring out where in the void it actually sits. The Cartwheel's elusive distance is a stark reminder that our map of the cosmos is still being drawn, and that every beautiful image hides layers of profound uncertainty waiting to be measured. Our most powerful supercomputers are trying to rebuild the Cartwheel from scratch. Phenomenon 18 is the fascinating struggle of simulations versus reality, a digital battleground where our theories face the ultimate test. Astrophysicists feed their best models into these virtual universes, programming in the laws of gravity, gas dynamics, star formation, and dark matter. They set the initial conditions, a spiral galaxy and a smaller intruder on a bullseye collision course, and then they hit start. The simulation runs, calculating the interactions of billions of particles over millions of virtual years. The goal is to watch the cosmic film play forward and see a perfect digital cartwheel emerge on the screen. Yet, time and again, the virtual result does not quite match the breathtaking reality observed by Hubble and Webb. The simulated ring might be too fuzzy, not as sharp and well-defined as the real one. The mysterious radial spokes may fail to appear or appear in the wrong configuration. The core of the simulated galaxy might end up too bright, refusing to become the faint, evacuated region we actually see. This persistent gap is not a failure, it is a beacon. It tells scientists that something is missing from their equations, an ingredient or a process they have not yet fully accounted for. Perhaps their models of how gas clouds collapse to form stars under such extreme compression are too simple. Maybe the role of magnetic fields, those invisible skeletons we discussed, is more crucial than anyone guessed. Or it could point to a deeper mystery in the behavior of dark matter, suggesting its particles interact in ways our current models do not predict. Each mismatch is a clue. The Cartwheel is not just a spectacle, it is a cosmic benchmark, a gold standard against which we measure our entire understanding of galactic collisions. Every time a simulation falls short, it forces a refinement, a tweak to the virtual physics, pushing our knowledge closer to the truth. This iterative dance between the digital and the real is how science progresses. The Cartwheel's perfect ring is a challenge, a beautiful, complex puzzle thrown at us by the universe, daring our most advanced technology to explain its every exquisite detail. The Cartwheel Galaxy is a time capsule from the universe's violent youth. Phenomenon 19 is its role as a local window into the early cosmos, a slow-motion replay of cosmic dawn happening right in our galactic backyard. To understand why this is so vital, you must picture the universe more than 10 billion years ago. It was a chaotic, crowded place far denser than today. Galaxies were smaller, gas was plentiful, and catastrophic collisions were a regular, almost routine occurrence. In that tumultuous era, the dominant mode of star formation was not the quiet, steady process we see in mature spirals like the Milky Way. It was explosive, ring-dominated, and ferociously efficient, exactly like the frenzy we are witnessing in the Cartwheel's brilliant outer ring. The Cartwheel is not an ancient galaxy from that time, but it is a perfect modern analog. It is as if the universe, for our benefit, recreated one of its earliest, most common processes in a galaxy close enough for us to study in exquisite detail. This transforms it from a curiosity into a Rosetta Stone. When the James Webb Space Telescope peers to the very edge of observable time, it does not see beautiful, crisp spirals. It captures faint, blurry, chaotic blobs of light, the infant galaxies of the primordial universe. Their structures are messy, their light is distorted, and interpreting what we are seeing is an immense challenge. Is that red blob a single massive burst of star formation, or several smaller galaxies smeared together by distance? Is its light telling us about calm growth or violent merger? This is where the cartwheel becomes our essential decoder ring. By studying its well-resolved nearby ring, we learn the specific signatures of a collision-induced starburst. We measure how much infrared heat its dust clouds produce, how its chemical makeup changes under duress, and how its light is distributed. We then take that detailed fingerprint and compare it to the faint, ancient blobs seen by Webb. If their light tells a similar story, we can say with much greater confidence that blob is not just a young galaxy, it is a galaxy undergoing a cartwheel-like catastrophe. It is a galactic collision in progress, seen across more than 90% of cosmic history. So every measurement we take of the cartwheel, every knot of star formation we map, every strange molecule we identify, is not just about understanding this one beautiful object. It is about calibrating our vision. It is about learning to read the violent, beautiful, and foundational handwriting of the universe's childhood, using a nearby, brilliant tutor to understand the faint, ancient whispers from the dawn of time. The cartwheel's brilliant ring is not a permanent monument, but a fleeting stage in an epic drama. Phenomenon 20 forces us to look forward, to ask what becomes of this cosmic pinwheel hundreds of millions of years from now. Based on our understanding of physics and the predictions of supercomputer simulations, a probable future begins to take shape. That dazzling outer ring, currently a compressed wall of gas and newborn stars, is still expanding outward like the ripple from a stone thrown into a pond. But unlike a water ripple that fades, this ring is expanding into the near vacuum of intergalactic space. As it expands, the density of its gas will drop dramatically. Star formation, which requires dense gas, will first become sporadic and then cease entirely. The massive, short-lived stars that currently light up the ring will have long since died in spectacular supernova, and the remaining, longer-lived stars will simply drift apart, their gravitational bonds too weak to hold the structure together against the relentless pull of the galaxy's rotation. The brilliant ring will not collapse, it will dissolve, its stars scattering into a vast, diffuse halo, leaving behind only a faint, ghostly smear of light. What then remains at the heart of this system? The inner regions, the ghostly inner ring and the disturbed core, will slowly begin to settle. The chaotic motions imparted by the collision will gradually relax through a process called dynamical relaxation, where gravitational interactions between stars act like a kind of cosmic friction, smoothing out wild orbits. The galaxy will not return to its original spiral form. That template was destroyed. Instead, simulations suggest it may evolve into a peculiar elliptical or lenticular galaxy, a smooth, football-shaped swarm of older stars with little gas left to form new ones. It will be a quiet, redder, and far more sedate object, a retirement home for the survivors of the catastrophe. However, the fate of this future galaxy is not set in stone. The presence of those companion galaxies adds a critical wild card. If a second merger occurs, it could inject a fresh burst of chaos, stirring up the settling stars and potentially triggering a new, though likely less dramatic, wave of star formation, resetting the galactic clock once more. This long-term view transforms our perspective completely. The cartwheel is not a thing, it is a process. We are not looking at a finished painting, but at a single, breathtaking frame grabbed from the middle of a film that is billions of years long. Its current beauty is the spectacular, fiery adolescence of a galaxy that will eventually grow old and quiet, its ring a brilliant memory written in the scattered motions of a trillion stars. The galaxy whispers its oldest secrets on a frequency our eyes cannot see. Phenomenon 21 is the unexplained radio loops and filaments, vast and ghostly structures that wrap around the cartwheel like the faded scars of a forgotten war. When astronomers tune their radio telescopes away from the chatter of visible light and X-rays, they enter a different realm of perception. Here, the brilliant ring often fades into the background and new, sprawling shapes emerge. These are not sharp, well-defined objects, but ethereal loops, faint filaments, and diffuse clouds that stretch across tens of thousands of light years, sometimes only loosely tracing the outlines of the optical ring. They are the cosmic equivalent of a lingering echo in an empty hall, a signal from a violence that has long since passed. So what creates these radio ghosts? Scientists have a few compelling suspects, each pointing to a different chapter of the galaxy's brutal history. The first suspect is the ancient fury of supernova. Over the millions of years since the ring formed, countless massive stars have lived fast and died young. Each supernova explosion does not just create a brief flash of light, it creates a colossal, expanding bubble of hot gas and magnetic fields, a structure that can persist for eons. These faint radio loops could be the fossilized shells of these ancient supernova remnants, now so vast and diffuse they have merged into one another, creating a faint, tangled web of past stellar deaths. The second suspect is the original collision itself. The gravitational shockwave that forged the ring would have generated immense turbulence and secondary shock fronts within the gas, disturbances that could have left permanent imprints in the galaxy's magnetic field and the distribution of high-energy electrons. These radio filaments might be tracing those fossil shock fronts, a permanent map of the pressure waves that once reshaped an entire galaxy. The third and most fascinating possibility involves a fundamental physical process, synchrotron radiation. This occurs when electrons, accelerated to nearly the speed of light by supernova shocks or other violent events, spiral around the lines of magnetic fields that permeate the galaxy. As they spiral, they emit a faint, distinctive radio glow. The presence of large-scale radio filaments would therefore be a direct tracer of two invisible things, the paths of relativistic electrons and the architecture of the magnetic fields that guide them. Studying these whispers is a monumental technical challenge. They are incredibly faint and spread over such a large area that teasing their signal from the cosmic background noise requires immense patience and the combined power of radio telescope arrays. Each faint loop is a puzzle. Is it a single, impossibly large remnant, or the overlapping shells of 100 smaller ones? Does its shape confirm our models of the collision's shockwave, or does it reveal a direction of energy flow we never anticipated? These radio ghosts are the Cartwheel's long-term memory, a faint but persistent record written not in starlight, but in the slow, spiraling dance of electrons in the dark. They remind us that the aftermath of cosmic violence is not a single event, but a series of fading echoes, each carrying a piece of the story that visible light has long since forgotten. Could a planet survive the birth of a galaxy? Phenomenon 22 is the search for planets in the Cartwheel's extreme environments, a thought experiment that pushes our understanding of cosmic resilience to the limit. We know planets form in the dusty disks around young stars, a process we have observed countless times in the quiet nurseries of our own galaxy. But the Cartwheel's outer ring is not quiet. It is a maelstrom of ultraviolet radiation, a shooting gallery of supernova shockwaves, and a gravitational roller coaster. The very forces that compress gas to create stars could also tear apart the delicate, swirling protoplanetary disks where worlds are born. Intense UV light from massive stars could evaporate these disks before dust has a chance to clump into planets. A nearby supernova explosion could blast away an entire solar system in formation, scattering its potential worlds back into the cosmic cloud. The gravitational pull from countless neighboring stars in those dense superstar clusters could destabilize orbits, flinging infant planets into the cold void of interstellar space. The odds seem impossibly stacked against something as fragile as a planet taking root, and yet the universe has a habit of surprising us with its tenacity. Consider the sheer scale. The Cartwheel's ring is forming stars at a rate hundreds of times faster than the Milky Way. Even if the success rate for planet formation is a tiny fraction of what it is in common neighborhoods, the sheer number of attempts could mean that planets do, in fact, emerge from the chaos. Imagine what such a world would witness. It would orbit a star within one of those colossal superstar clusters. Its night sky would not be dark, but perpetually aglow with the combined light of hundreds or thousands of neighboring suns, a permanent, soft twilight from the surrounding stellar city. The concept of a truly dark night would be alien. The passage of comets and asteroids might be far more frequent due to gravitational stirring, leading to a violent early history. But if a planet could cling to existence, if it could find a stable orbit in that gravitational dance and retain an atmosphere against the stellar winds, it would represent the ultimate triumph of cosmic order over chaos. This search is more than speculation. It is a fundamental question about the conditions for life. We often ponder life in calm, sun-like star systems. But the Cartwheel forces us to ask, could biology ever gain a foothold in the universe's most violent and irradiated neighborhoods? If planets can form and persist here, then they could form almost anywhere, even in the furious hearts of colliding galaxies in the early universe. The potential for life, therefore, might not be limited to galactic suburbs, but could extend even into these brilliant, deadly metropolises of stars. The Cartwheel challenges us to expand our vision of what is possible, to consider that even in the aftermath of catastrophe, new worlds might quietly be taking shape. The collision that forged the Cartwheel was not just a spectacle of light, it was a tremor in the fabric of space-time itself. Phenomenon 23 is the realm of gravitational wave forensics, a future science that could one day let us hear the echoes of that ancient catastrophe. When two galaxies collide, their supermassive black holes, millions or billions of times the mass of our Sun, are dragged into the heart of the chaos. As they spiral inward, locked in a final, deadly dance, they warp the very geometry of the universe around them, sending out ripples in space-time known as gravitational waves. These are not waves of light or sound, but literal stretches and squeezes in the distance between objects, a vibration in the cosmos itself. The initial bullseye collision of the Cartwheel would have generated a tremendous, short burst of these waves. But the more tantalizing signal would come from what happened next if the black holes merged. Did the intruder galaxy's central monster plunge into the Cartwheel's core and combine with its own, creating a single, even more massive gravitational anchor? Or are they still orbiting each other in a silent, slow waltz at the galaxy's faint heart? This is where future observatories like the Laser Interferometer Space Antenna, or LISA, enter the story. Planned for launch in the next decade, LISA will be a fleet of 3 spacecraft flying in a giant triangle millions of kilometers apart, using lasers to measure distances with insane precision. It is designed to listen for the low-frequency hum of merging supermassive black holes, a bass note in the cosmic symphony that ground-based detectors cannot hear. If a merger happened in the Cartwheel, LISA might one day detect the faint, lingering whisper of that event, a signal that has been traveling through the universe for hundreds of millions of years. This transforms the galaxy from a visual mystery into an acoustic one. It becomes a cosmic crime scene where we could finally collect the gravitational fingerprints of the perpetrators, not by looking but by listening. The precise frequency and pattern of those space-time ripples would tell us the exact masses of the black holes that danced, the timing of their final collision, and the spin of the resulting behemoth. It would be the ultimate closure to the whodunit, providing a physical record of the violence that written in the language of gravity itself, a direct and immutable testimony from the moment the ring was born. The Cartwheel's dark matter halo is not a quiet, symmetrical shroud. Phenomenon 24 is the search for anomalies in this invisible scaffold, a hunt for distortions that could rewrite the rules of the cosmos itself. Every galaxy, including our own Milky Way, is embedded within a vast spherical cloud of dark matter, an unseen gravitational anchor that dictates how stars and gas move. We infer its presence because galaxies rotate too fast for the gravity of their visible stars alone to hold them together. Something invisible must be providing the extra pull. In a normal, undisturbed spiral, this dark matter halo has a predictable, smooth distribution, but the cartwheel is anything but normal. The bullseye collision would have been like dropping a boulder into a still, dark pond. The gravitational shock would have sent ripples not just through the visible gas, but through the invisible dark matter as well. This could have stirred the halo into a lopsided, asymmetric shape, perhaps stretched in the direction of the intruder's escape or compressed in a ring-like structure that mirrors the visible one. Astronomers are now searching for the fingerprints of this stirred dark matter by studying the motions of stars and gas in the cartwheel's outer regions with extreme precision. If the rotation speeds or the paths of star clusters deviate from what a smooth, spherical halo would predict, it points directly to a dark matter distribution that has been violently rearranged. This is where the mystery deepens beyond simple stirring. Some theorists propose that the anomalies might hint at something even more exotic, interactions within the dark matter itself. Our standard model assumes dark matter particles are cold and collisionless. They pass right through each other and ordinary matter like ghosts. But what if, under the extreme conditions of a galactic collision, dark matter particles could interact even slightly through some unknown force? This self-interacting dark matter would behave more like a fluid, creating drag, forming wakes, and smoothing out densities in ways that could explain subtle features in the cartwheel that cold dark matter cannot. The galaxy thus becomes a unique, natural laboratory. We cannot create dark matter in a lab on Earth, but we can observe how it behaves under the most extreme gravitational stress tests the universe can provide. Every strange wiggle in the rotation curve of the cartwheel's outer ring, every star cluster moving on an inexplicable path, is a potential clue. It is a message from the invisible 95% of the universe's mass, written in the subtle motions of the 5% we can actually see. The cartwheel's beautiful rings are, in this light, merely the visible tip of a much deeper and darker iceberg, and its true shape remains the greatest puzzle of all. Its final and most humbling truth is that it is not unique. Phenomenon 25 is the cartwheel's place in the galactic zoo, a single, brilliant specimen in a small but fascinating collection of cosmic oddities. When we zoom out, we find that the universe has crafted a handful of these ringed structures, each with its own story and personality. Compare it to Hoag's object, another perfect circle of stars. But where the cartwheel is a seething, star-forming riot, Hoag's object is a portrait of serene, ancient calm. Its yellow core is classic, its blue outer ring is composed of older stars, and the vast gap between them is eerily empty. No shockwave expansion is at work here. Its origin remains one of astronomy's quietest mysteries, possibly the result of a long-ago, gentle accretion event. Then there is the Lindsay-Shapley ring, a fainter, more delicate loop that appears to be the result of a very specific kind of gravitational tug. A direct collision where a smaller galaxy passed right through the disk of a larger one, much like the cartwheel, but perhaps with different speed, angle, or gas content, leaving a simpler, more ghostly imprint. This comparative study reveals a profound truth about cosmic evolution. It is stochastic, ruled by chance and minute details. The precise angle of impact, the relative sizes of the galaxies, the amount of gas present, even the timing of a second encounter, all of these variables conspire to create wildly different outcomes from the same basic recipe of collision. So what elevates the cartwheel to its status as the textbook example? It is the perfect storm of visibility and activity. Its rings are shockingly sharp and well-defined. Its star formation is ferociously bright, lighting up the entire structure across multiple wavelengths. and its story is written clearly in the surrounding chaos, with visible companion galaxies and radial spokes that point directly to its violent origin. It is not the only ring galaxy, but it is the one shouting its history from the rooftops of the cosmos. Studying this galactic collection does more than satisfy curiosity. It teaches us about the menu of possibilities. It shows us that a single physical process, a galactic collision, can produce a spectrum of results from Serene Hogue's object to the furious Cartwheel. This transforms our understanding of galaxies from fixed types into dynamic stages in a life cycle, temporary forms assumed during moments of incredible stress. The Cartwheel is not a freak, it is a key. It is the Rosetta Stone that helps us decipher the quieter, more cryptic rings elsewhere, proving that the universe, in its infinite creativity, uses catastrophe as a brush to paint not one masterpiece, but an entire gallery of strange and beautiful forms. From a single, perfect strike to a gallery of cosmic ghosts, our journey through the Cartwheel Galaxy has revealed a universe of chaos dressed in a ring of light. We have traced the ripple of a collision that erased a galactic core, walked the invisible skeleton of dark matter spokes, and stood before cosmic powerhouses blasting through the laws of physics. Each of these 25 phenomena is a thread in a single, sprawling story of destruction and rebirth. The Cartwheel is not a serene portrait for a telescope's gallery. It is a dynamic, messy, and profoundly informative cosmic laboratory. Its very existence challenges our neatest astrophysical theories, forcing supercomputers to rewrite their code and scientists to question their assumptions about everything from magnetic fields to the nature of dark matter itself. This galaxy is a teacher, using its beautiful catastrophe to instruct us on the violent processes that built the early universe and that continue to shape the cosmos today. Yet for all we have uncovered, this is merely the opening chapter, with the penetrating infrared gaze of the James Webb Space Telescope already peeling back the dust and the upcoming Vera C. Rubin Observatory set to scan the entire sky nightly, hunting for transient flashes within the ring. The Cartwheel's deepest secrets are just beginning to unravel. Its mysteries will continue to guide us, a perfect ring spinning in the dark, reminding us that the universe's greatest wonders are often born from its most violent moments. So tell us, which of these 25 bizarre phenomena captivated you the most? Was it the ghostly inner ring, the impossible X-ray sources, or the haunting question of planets born in a storm? Share your thoughts below, and if you crave more journeys to the edges of our understanding, be sure to subscribe for the next deep dive into the cosmos's greatest mysteries.